The next thing we're going to look at here is the derivatives of inverse functions. And really, one thing to know about this as we go into it is there is technically just a quick formula that you can memorize, but if you do your best to understand where that formula comes from and how it works, it helps to prevent you from making mistakes or by misremembering the formula. If you can kind of think through what we're doing. And so that's what I'm going to emphasize in this first part, is just thinking through what are we doing and where does it come from. So first we want to talk about just inverse functions in general, and I just want to point out how these things are related, because that will then help us to figure out how their derivatives are related. So what you'll notice is we have two functions, f of x and the inverse function of x. And if you remember, the relationship between a function and its inverse is just switching all of the x and y values. In other words, it's reflecting it across the y equals x line. So if we switch our x and y values, then, for example, this point right here is a f inverse of a. So they're writing this point with respect to the inverse function. That means there's an equivalent point over here that's f inverse of a and a. If all the x and y values are switched, then any changes in the x, y values are also switched. So if there's these slopes, the p's and the q's, which are just the change in x, the change in y. So in this example, the p is the change in x, but for the inverse, it's the change in y. The q is the change in y for the function. The q is the change in x for the inverse function. And then as a result, you'll notice that that means also their slopes are going to be 1 over each other, right? The slopes are just the switches of the x and y values. So if we're always thinking about flip-flopping x and y values, but what's important is realizing that they're for these equivalent points, which is switching the two locations. So let's summarize all of that here. So first of all, the x and y values swap between a function and its inverse. That also means that delta x and delta y values swap for a function and its inverse. And by a result, this means the slope of related points also invert. Now these aren't for the same x value, they're for these related points here and here. In other words, for a and f of a, or in this case, a, f inverse of a, and then on the original function, f inverse of a and a. Again, switching those x and y values. So if we combine these rules, we get the following. The derivative function, the derivative of the inverse function at point x is equal to, or if you prefer f, that's written weirdly. If you want to write it with prime notation, you can do it like this. F inverse prime of x is equal to 1 divided by the derivative of the original function of the point of the inverse function evaluated at x. So what we're trying to do here is f inverse of x is giving me this f of a point, right? So if I plug in a, I get f inverse of a out here. So this is basically giving me, quote unquote, an a value. Let me not write it that way because that's looking confusing. So if I have a value a, or in this case a value x, then I get out, when I plug in the function, this f inverse of a. Then over here, to find this slope at this point, I need to plug in this x value. Well, this x value is going to be the y value of my inverse function. So that's why I plug that in to my derivative, because you'll notice the derivative here is going to be the derivative of this point is the function, the derivative of the function with the inverse value plugged in, and that gives me q over p, and that's 1 over what I actually want, which is this slope here. This one's a really weird one. It's also hard to explain because it's values flipping and flopping and back and forth, but it's something that you just kind of need to practice with and see some examples, and that should help. So let's look at one such example. G of h of x are inverse functions of each other. Given the following values, find h prime of 3. So h prime of 3, you'll notice we don't have h prime on this table, so there's no way to just look at the table and find it directly. But we know that h prime is also equal to g inverse prime of 3, because h and g are inverses of each other. And now from before, we know that g inverse of 3 is going to be equal to 1 over g of the inverse value at 3. So this is just using the equation from before with way too many parentheses. So I want to find g prime, or g inverse of 3, because that will tell me kind of where on g is my equivalent point. So g inverse of 3 is going to be what h value, or if you prefer, g of h of 3, is what h value gives me 3 out. So h of 3. So if we look, h of 3 is going to be 4. In other words, if I put 4 into g, I should get 3 out. And so we see those match up. So I want h of 3, which is 4. So this should be 1 over, and then g of h of 3. We said h of 3 was 4. And, oh, this should have a prime, sorry. And g prime of 4 we see as 1/2, so this is 1 over 1/2, which is in fact 2. So the h prime of 3 should be 2. Again, it's just a weird thing that you have to play with until it makes sense, kind of looking at the flipping back and forth. It's also something that we can talk through and work through in class, and that'll be a little bit easier than trying to get it just from the video here.